I should put a triple equal. You guys know what I mean when I say triple equal? Triple equal or colon equal for me is saying more. No. The first one is not a triple equal. The second one is a triple equal. It is more than just is equal to, I mean, is equivalent to, is defined as, is an always true definition. This on the left is F equals ma. This on the right is to say A is the slope of velocity. Slope of velocity is the meaning of A. F equals ma is a physics equation with cause and effect. Delta phi over delta t isn't, it is always true. It is a fundamental law of nature. No one has discovered an exception to this, but it's not the meaning of voltage. Voltage is what? What's voltage? Anyone who says IR gets pretend smacked it. Not charge over time, that's current. That's voltage. Google question C. Do you remember what volts means? What is the meaning of voltage? Core equation. Don't look. I want to see what you know. The meaning of voltage, I'll give you a hint, is not what we just did. Okay, time's up. You either know it or you don't, if I'm asking for memory. Energy divided by charge. Energy per charge. Charge per time is current. Yeah, okay. So. Let's do a couple of examples to prepare you for your homework and quiz. I mean, giving you the answers in advance, and also to make sure that this makes some kind of sense to you. Here's an example from the homework. I'm not going to give you exactly the same numbers, but if you could do this, you could do that. Suppose I have a loop. I have a loop of wire. I'll form it into a rectangle because the math is way easier. And it's, what the hell? 3 meters wide by 2 meters tall. And I bathe this whole sucker in a magnetic field. You remember the crosses? The X's? What's the X mean? That's out of view is into the page. You pointed right, you said it wrong. The magnetic field is, I don't know, 5 Teslas? Find me the flux. What is the flux? Through this loop. You have to be precise. You can find the flux through lots of things. Find the flux through this loop. Maybe I'll color this different. And I will remind you, by the way, of the equations that we just had on the board. Induced voltage is rate at which flux changes, and flux means field times area. I want you to find the flux. What is phi? Multiply carefully, my friends. I mean, as a father, I can tell you that you should multiply carefully. Yes, question. It does, the Weber. The Weber, WB. But for us, I tell you the Weber. Are you an MCAT student? Okay. Teslas times square meters. Teslas meters squared. And I'm going to say times up. Muy bien, very good. You found the area. Presumably, you found the area is 2 times 3 is 6, not 5. Area is product of multiply, don't add. And then magnetic field, B times area, is 5 times 6 is 30. Good. Let me give you a different one. Here, real fast. I'm going to give you an equation for a magnetic field. I'm going to say the magnetic field is small. It starts out as 1 Tesla, and every second it ramps up by 3 Tesla. Don't get T confused for Tesla. This T is time. The unit T is Tesla, is the unit for the capital T is the unit. So what I'm saying is magnetic field starts at 1, and after 1 second it's 4. After 2 seconds it's 7. After 3 seconds it's 10, so on and so forth. Can you find for me, Google question E, test yourself, can you find for me the flux after 3 seconds, and can you find for me the voltage induced in the loop? So what is this? Questions E and F. Test yourself. You're doing great. Find the flux at time, 3 seconds, and find the induced voltage. All you got to do is apply the equations. Can you apply the equations? All right, here we are going to practice. Before we dive into lens, this is important. Okay, let's work it out. If you'll forgive the disgusting joke, as the joke goes, how does a constipated mathematician figure out a problem? You know what? Maybe I'll leave that as an exercise for the student to deduce the kind of disgusting punchline. Okay, so numero uno, half of y'all have got it. Good. 60. 60. How do you find the magnetic field at time, 3 seconds? Voila! You find the magnetic field, 3 times 3 plus 1 is 10 Tesla at that time. And the magnetic field times 2 times 3, 6 meters squared is indeed 60. 60 Webers, or I usually write Tesla meters squared because, I don't know, I don't like the Weber. So the correct answer for question E was indeed 60. If you got that, pat yourself on the back. Let me pause for a question here. If you ain't got Webers, if you ain't got flux, the rate of change of flux is harder. No one wants to ask me a question? Oh, you're in good company if you missed. Half the class missed. Yes, absolutely. So here's how I find really sort of kind of anything in physics. I look, if I want phi, I look for the equation for phi, the core equation for phi. Phi has 2 parts, b and area. Well, b is hard, so let's just do b times the area. Let's look at the area first. The area, God willing, is simple, right? 2 times 3 is 6. And now I need to figure out what the magnetic field is. In particular, I told you the magnetic field is an equation now. It's an equation that changes, it's a value that changes as time progresses. So the equation for B is 1 plus 3 times time. And then what I tell you about time, I'm asking you after 3 seconds, what is the flux? That means I just plug in 3 for time. I mean, that's the kind of the whole idea of algebra. Okay, 3 times 3 is 9, plus 1 is 10. And 10 times 6 is, rumor on the street has it, 60. So far so good? Yeah? Any other questions about finding the flux and why and how and what and stuff? Okay, now the slope, we had one correct answer? No, we need more than that. We need more than one correct answer in the class. So let's talk about the slope here, the rate at which phi changes. There are multiple correct ways to do this, and some of them going to make more sense for some people, and some of them are going to make more sense for other people. I'm going to give you a couple of ways to do this. First off, let me point out that, well, let me write down area equals 6 square meters. Magnetic field as a function of time is 1 plus 3t. And our goal is to find the voltage using Faraday's law. I'm going to make space for myself. Okay, so, what's the law? Lay down the law. The rate of change of flux, and flux is area times field. The big mistake that I think most of y'all made is to say, I know what the flux is at 3 seconds. The rate of change of flux must be flux divided by time. No, niet, nein, nichts. Listen, consider the following. If I'm 60 miles from my house and I walk, after an hour, I'm at 61 miles from my house. Does it make sense to divide 61 by 1 and say I went 61 miles an hour? Does it make sense? If you go from 60 miles from your house to 61 miles in your house, you're crawling along the ground, 1 mile an hour. You go 1 mile in 1 hour. Why 1 mile? We don't divide the position by the time. We divide the change in position by the time. So we do not ask what is B at 3 seconds. We ask the rate at which B is changing. One way to find the rate of change is, do you know what slope of a linear equation is? I see slope in this equation as whatever multiplies your independent variable, whatever's multiplying your t. The slope is 3. Look, I mean, you got y equals mx plus b. What's the m? The m is the thing that multiplies x. The slope is the thing that multiplies your independent variable, in this case time. Maybe you don't like that. Maybe you don't like the idea of looking for that which multiplies by t. If that doesn't click for, if that doesn't click for you, let's build this in a different way. Here's a more follow your nose approach, perhaps. What the heck does delta always mean? So let's plug in phi at 4 seconds and phi at 3 seconds and find out how phi is changing. What is flux at 4 seconds? $78. 1 plus 3 times 4 is what? Not times. Oh, hold on. One step at a time. 1 times 3 times 4 is 13. 1 plus 3 times 3 is what? We are not looking at the slope at 4. We're looking at the change from 3 to 4. So if I find that the slope started at 10 and ended at 13, what's my change? 3 Tesla meters squared. The change in flux is 3 Tesla meters squared. Now, what's the slope? The slope is the rise over the run. The induced voltage is the change in flux, 3, divided by the change in time. What's the change from... Thank you. This is B. I should be multiplied this by area everywhere. That was a test to see if you were paying attention, and you passed. Okay, so the magnetic field is the equation that I just wrote. We're going to multiply each of these by a factor of 6. Okay, so 6 times 3, 6 times 13 minus 6 times 10 is 6 times 3 is 18. Okay, so the change in flux is not, change in flux is not, it's 18. 6 meters squared times 3 Teslas per second. Okay, now what's time? Change in time here. I did from time 3 to time 4. That's 1 second. Nope. Yep. Perfect question, which leads exactly to my next point. How'd I get 3 and 4? It doesn't matter at all. If you've got a constant slope equation, the slope between any 2 points is the slope between every 2 points. Pick a number, my friends. Any number whatsoever. Like a small integer, please, so I can multiply. 8, great. Is 8 where it's starting or ending? Ending. It ends at 8 seconds, and a number smaller than 8. 3 seconds, great. Oh, 3 seconds is great because I already calculated that. That's 60 Webers there. Okay, so what's B at time 8? 3 times 8 is 24, plus 1 is 25. Okay, so I do 6 times 25 minus 6 times 10. Ah, I don't like doing that. I like factoring out the 6 and saying 25 minus 10 times 6. 6 times 15. What's 6 times 15? Yeah. 3 times 30. Yeah, good. Okay, so that's 90 Tesla meters squared if I go from time 3 to 8. What's 8 minus 3? Last I heard it's 5. What's 90 divided by 5? Oh, it's the same number, same voltage, same answer. EGADS. I'm going to give you a third example. Let's calculate the flux at time 0. What do we start with at the beginning? The flux at time 0 is 6 meters squared times 1 Tesla. 6 Weber, 6 Tesla meters squared. After 100 seconds, what's the flux? Area don't change. 301. Okay, 300 times 6 is 1800. Plus 6 times 1, so 1806. You can check me on a calculator if you don't believe me. Oh, my sweet baby Jesus. Look, the change in the flux is 1806 minus 6 equals 1800 Tesla meters squared. Change in flux over the change in time. Rumor has it 1800 divided by 100 is 18 volts. Oh, my sweet baby Jesus. So it doesn't matter. Make up any numbers you want. Anything at all. And you can find the rate at which flux is changing. And one more time, let me emphasize. Did we plug in the flux at a time and divide by the time? Niet. No, nein, nicht started. No. You can't just divide the flux by the time to get to there. You have to divide the change in flux over some interval by the interval. Okay. Let's see if that made sense. Here. Here's another. Here I've got flux going, field going in, and field coming out. What do you think that does? Partially canceled, exactly. 2 Teslas in and 1 Tesla out, they're going to be opposite directions. They will cancel out their overlap. The hint is calculate the flux from the in part, calculate the flux from the out part, and subtract them. Hey, just start by calculating phi. And show me in G. You don't like this. Tell me why. Ask me a question. To calculate the area, you have to say, well, I've got 2 different magnetic field regions. The magnetic field times the area of that field is the flux through that part. Use the area of the part that has the 2 Teslas. Use the magnetic field of the part, use the area of the 1 Tesla region to calculate that flux through that part. Question? So you'll add them, but one of them is in the opposite direction. So one of them has a minus sign. Yes. Doesn't matter which because we haven't defined the direction of flux. I will guide you on the left. Oh, don't look if you aren't done. I put the answer up, but don't look until you're done. Spoilers. Spoilers, sweetie, as Doctor Who said. River Song. Whatever. Okay, I'm seeing a problem in converting centimeters to meters for half the class. Let's review that real fast. 20 centimeters times 20 centimeters is 0.2 meters times 0.2 meters. So 20 centimeters squared is the same thing as 0.20 meters times 0.20 meters. That is not 4, and that is not 400. That is 0.04 square meters. I think a problem that at least some people, problem that always somebody has, is first you multiply 20 times 20 equals 400, and then you say, all right, this is in centimeters squared. I'm going to pretend that centimeters squared means centimeters. 100 centimeters and 100 square centimeters in a square meter. Divide by 100, I get 4. No! I challenge you. Go to the store, buy 100 little thumb-sized tiles, then tile my bathroom. I have a really small bathroom. It's about a meter square. Do you think 100 little thumb-sized tiles can fill this entire area? No. 100 makes a line across the bottom. You need 100 lines to make, you have to look at the conversion along each axis. Your square centimeters is not 100 square centimeters to 1 square meter. It's 100 squared centimeters to 1 square meter. Actually, only a couple people made that mistake. The other part, so far so good? Do you want one more about finding flux? No? Move on? Okay. Yester class. Now let's hit Lenz's law. We're going to hit these in a second. I want to hit, no, I don't want you to see it and be looking at that while thinking through this. The bestest way I have found to break down Lenz's law, there's a sentence I'm going to show you in a little bit. You can write it down. You can break it apart. But if I show you that immediately, you're going to turn off. 4 parts to the sentence. There are 4 steps. Jean-Luc Picard said there are 4 lights, so let's count to 4. Here are the steps. Find original flux. Find the original flux. Step 1, find the original flux. Step 2, is the flux increasing or decreasing? Step 3, the reaction to this is to oppose the change. The reaction flux, it's my term, I haven't seen that written down. The reaction flux opposes the change. And step 4, you work backwards from finding the direction of the reaction flux, and I'll teach you this today. Go backwards from finding the direction of the reaction flux to the current that caused it. Yeah. Uno, find the original flux. Dos, how is it changing? Trace, which direction would oppose the change? I want to keep it what it was. How do I oppose the change? 4, what current causes that reaction? You don't know how to do 4 yet. I'll teach you how to do 4, but that's where we're going. Okay. Let's do an example about finding at least steps 1, 2, 3. So field is kind of, sort of, not really, a little bit like force. And area is area. I'm going to push on this table, and I want you to tell me which direction of a push would you have to oppose the change that I'm making. Okay, so I'm going to push harder and harder and harder and harder and harder on this table. Which direction would you have to go to oppose the change? I am increasing my downward force. To oppose me, you have to push up. Yeah. Okay, now I'm gradually decreasing the force I am pushing down with. Which direction do you have to push to keep the force the same? Downward. Muy importante, downward. I am taking off my down force. If you want the table to feel the same thing, you've got to be applying a down force. Okay, now I am walking to the right. Imagine that there's a big wire around me. I'm walking to the right through the wire. I am a current. I'm a magnetic field, sorry. I'm a magnetic field walking to the right through a loop of wire around me. And I am walking faster and faster and faster and faster. I'm giving more and more oomph to the rightward direction. Which direction opposes that increase in rightward flux? Now I'm walking left and slowing down. How do you oppose a decreasing leftward motion? You go in the same as the original. Good, 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 good. In general, you could say, if that is not clicking, you could say, if the field is strengthening, opposite direction. If the field is weakening, same as the original direction. For short. Here's the full sentence. The direction of the induced current, the reaction current, the current caused by voltage induced, is such as to make its magnetic field oppose the change in the current, in the flux that induced it. Pick it apart, one word at a time. Flux that induced it, that's the original flux. How is that flux changing? Well, that's step 2. Opposes the change, that's step 3. Find which way opposes that change. Last thing we have to do is understand how to find the direction of the current that makes a given flux. Okay? Feel better? Feel okay? Feel good? We need to do step 4. I need to teach you how to find which way a current makes a field around it. This, I feel like y'all are doing better. Maybe I'm explaining it better. I don't know. Maybe you guys are better geometry thinking than last year. I feel like y'all are doing better than my class was at this time last year. With this topic, at least. Let me ask you this. I'm going to give you guys a choice because they also died at this section. There are 2 ways that I could proceed. I could show you how everything is one right-hand rule, or I can introduce variants to the right-hand rule that involve less thinking. But then you've got to know multiple forms of the same thing. You want one right-hand rule that involves multiple steps, or 3 right-hand rules that are 1 step? First one. You vote the second one. Okay, show of hands. Who wants 1 right-hand rule with 3 steps? Who wants 3 right-hand rules that are each 1 step? Okay, I could try. Okay, I will remind you that the right-hand rule, 1, 2, 3. Well, no, we don't put 2 in the same direction. We stick it out or use the palm of your hand. 1, 2, 3. Whatever I put first is the first finger. Whatever I put second is the middle finger, or the palm if you don't like to give people the finger. And your thumb shows the result of that. Okay. The right-hand rule for finding the direction that a current generates a field is as follows. The direction of the current the direction of the current. Yeah, I need the next slide here. Here's the one and only right-hand rule. This is next week. The direction of the field. You guys okay with me writing a vector sign on top to say the direction of? Vector sign means direction of. I'm going to say, no, I shouldn't say wire direction. You can always find the direction, the magnetic field that a current makes. All magnetic fields come from currents, ultimately. You can find the direction a current makes its magnetic field by doing which way is the current pointing, first finger, first vector, and which way are you pointing to point at that field, second finger. Let's do an example. Out of the page or right? Out of the page. Here is some current. Current is coming out of the page. I am a wire. I am shooting current at you. Pew, 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 pew. Which direction does your first finger go? Back of the classroom, right? Back of the classroom. That's the direction of the current. The second finger is a little harder. We say some bit of current makes some magnetism. We have to identify where we want to know the darn field. Let's find the field here. I want to find the field. Maybe I should, if I put a point, that'll look like an out of direction. Oh, crap. I'm going to find the field to its right. What I mean by field position is put your brain at the current and then point at where you want to know the field. So, for instance, if I am this piece of current, which way do I have to point to aim at where I want to know the field? This way, to your right. Okay, so the first finger, the second finger, or thumb if you prefer, the result is up. Sorry? Palm is your middle finger or middle finger is your middle finger? There are multiple ways to say it. I mean, your palm or stick your middle finger out. Same thing. Up. So where is the field? The field we just calculated is there. Magnetic field on the right-hand side of a little bit of current coming out of page is up. What about on the left-hand side? First finger is the current direction, always. Second finger is which direction you point your hand, if you are the current, to point where you want to know the field. Third is, all right, if I'm looking on the left side of the wire, then that direction is down. Magnetic field over here is down. I'll test you another. Ask you this. If you want to know the field, what is the field here? Above the wire? You tell me. Google question, whatever is next. Oh. Which direction is the magnetic field at this point? H. Google question H. What is the direction of magnetic field due to that current at a position above the wire? Correct and correct for the first two respondents, correct for the third respondent, correct for the fourth and fifth. Incorrect, incorrect. Did we do palm or middle finger? I flip it every other year. Palm, okay. I heard people groan, at least one person groan, when I put out my second finger. Or is that the part that screwed you over? Whoever groaned. Face the direction where you want, of the point you want to know about. And then the third finger, the resultant, the thumb pointing left. Are you okay with that being the direction of the field at that point? And you're all using your right hand, yeah? Common beginner goof. As it happens, if you calculate the magnetic field at lots of positions, magnetic field makes little circles. What the hell? I'll teach you the other way to do this. The other way is to say that if the current is straight, the field is curved, and if the current is curved, the field is straight. In this case, I've got a straight wire I described. Your thumb is the straight part. Your fingers curve around your thumb in the sense of the field. So if I put my thumb sticking out, then which direction do the fingers of my right hand curve naturally? They curve in the, from this perspective, counterclockwise direction, yeah? You like that better? You may use that. You like it worse? Use the first. They are equivalent mathematically. Okay, what if I have a coiled piece of wire? Here I'm going to do an end-on view of a coil of wire. Whoopsie, you can't turn around. Okay, so here is an end-on view of a little piece of wire where current is flowing, for the hell of it, counterclockwise, clockwise. Second way, first, if you curve your fingers, curve the fingers of your right hand without breaking your fingers in the direction of the current, your thumb shows the direction of the field, in this case. So if you got a curvy current, make the curvy the part of the fingers, vice versa. If you want to do it the first way, second, find the direction of current cross the direction of field position. Wait, hold on a second. The current points in lots of different directions. Here it points down left, here it points left, here it points up left, here it points up right. Pick any point and find the direction of the field due to that point. They will all add up. I will tell you that all the field ends up being in the middle of a circle of current. So outside, there is no field out here. Let's do at the middle. Let's find the direction of field at the middle point. I'm going to pick, without any reason, the direction of current here is the down left. I'm going to analyze this bit of current's effect. If I point my first finger down left and my palm, aka middle finger, in the direction of where I want to know, point, this bit of current is contributing an in-field, exactly as I said with the other method, an in-field contribution. How about over here on the left side? First finger current direction, second finger, aka palm, facing where you want to know, that's to my right side, direction of the field contribution in. Okay with this? Sure. Curly goes with straight, straight goes with curly. Fingers of a hand curl, and thumb goes straight, right? The fingers of your right hand. No, don't move your thumb. Just rotate your fingers around your thumb. This is the sense of the curly. Yes, you always have to stick out your thumb, right? If you want to get a ride. So for current to field, for a straight current, put your thumb in the direction of the current. Okay, now look, curve your fingers now. Which direction are they curving? Which direction are they pointing? Schlink, schlink. You like that better? No? It's fair. It's fair. If you can't see that this is counterclockwise and that this is clockwise from your perspective, that's fine. Use the first method. Questions about this? Either. So if my field, if I'm looking at, wait, the second method. You want the second method? Arrange your fingers so that the curly arranges in the, from this perspective, clockwise sense. Which direction is your thumb pointing? Stick that thumb out. Yeah. Infield, field. Now there are equations to find the magnitude of the field because of a current here, there, and everywhere. But I want to keep this as straightforward as possible. I'm just going to tell you that if you increase the current in a piece of wire, the field gets stronger. If you decrease the current in a piece of wire, the field gets weaker. If you get closer to a straight wire, the field gets stronger. If you go further from a straight wire, the field gets weaker. If you've got a couple of loops in here, if the loops don't form a spring that goes on forever, then the closer you get to the plane of the loop, the stronger it is. In lab, you'll have coils of wire, and you'll have a bar magnet, and you'll shove the bar magnet into the hole of the coils of wire. Which direction is that, getting a stronger field or a weaker field? If you run an electricity through the coils of the wire, the field due to, whoa, I actually said it backwards. I said something that would induce that. No, if you run electricity through a circle of wire, then the closer you get to it, the stronger the field is going to feel. And of course, increasing the current. There is an interesting thing. If this current forms a spring that goes on, wrapping around in a cylinder, like wrapped around a cylinder for a long, long time, the field inside is actually constant, doesn't really depend on how deep into the solenoid or where in, this is called a solenoidal shape, where in the spring you are. As long as you're contained within the volume of that cylinder, stays constant. You will also see that in lab. That is not a foundationally important thing because I'm not testing you on the equations for magnetic field in here. I'm not going to talk about why, but let me just put this out there. A way to make the magnetism really visible, what you will do in lab, pointing this out, if you put a piece of iron, something magnetizable, nickel, cobalt, iron, inside a electromagnet like this, the magnetism goes crazy big. So in lab, you will also be shoving things in. Oh, hey, it's almost as if the magnetic effects of a circuit component, electromagnets are circuit components, depend on the geometry, the size and shape, and the materials. This is a new kind of electronic component, although we're not going to get into how to apply it. Okay, let's do a calculation with this, which is also Merry Christmas, I'm giving you a quiz answer. You're welcome. I'm going to tell you that we've got a coil of wire, which is passing current, what the hell? Passing current clockwise, but getting weaker. So I've got current decreasing. Which direction is the flux in the plane of this loop? In or out? Nope. Yeah. Or in on the inside? Yeah. Okay, so the flux is in. Is the flux getting bigger or smaller? Weakening. If I decrease the current on the electromagnet, I've got less electromagnet. If I've got a weakening in field, what do I want what do I want to do to oppose that change? More infield. Doesn't have to be more weakening. You want stronger infield. Okay. The final question is, how do I replace in-field? What direction must the current go to get an in-field? The reaction, voltage, the effect of the magnetic field made by a current pushes on the original current. The last question is, how do we make a field which pushes in, makes an in flux, to counter the loss of flux? Which direction must the current go? Same as the original or opposite? Same. This is a general rule of thumb. In every case that I've seen, although this isn't like a law that I've ever been taught, every time I've ever seen this, the rule of thumb is magnetism opposes changes. The current is decreasing. The magnetic field is going to put a voltage on to try to oppose that loss of current. Good. Now, a different one. I have two coils of wire. I pass, here's a perspective drawing. So I've got like two hula hoops here. This is the front side, this is the front side, this is the back side, this is the back side. Maybe I should draw them more foreshortened. Yeah, there we go. There we go. The smaller arrows are showing that that's further, that's the side of the coil that's further away from you. Can you visualize this now? So the current is going up the back and down as it comes out of the paper. Does that make sense? My question to you is, this current in the original loop is going to make a flux that'll pass through this loop. I'm going to walk you through how to reason through this. Suppose we increase the current in the first loop. I'm going to increase the original. I want you to tell me the direction of flux in second loop. Here's steps 1, 2, 3. I guided you. Find the direction of the flux from the original current, from I1. Find the way that that is changing. And then I want you just to tell me which direction should the flux be, left or right, for all of these. Which way opposes that change? I'm increasing the current in this left loop. What do you do? Where does that go? These are Google questions. What? Where are we? Well, the IJK. Thank you. From my perspective, just for what it's worth, looking end on over here, I see the current going clockwise. That helps. And clockwiser and clockwise. You visual that? The big arrows are closer. Yeah. So it's going down on my right, up on my left. It's away from me into the plane of this, yeah. Now, from your perspective, is that into or out of? I'm sorry, is that left or right through the second coil? Rightward. Field, the flux, from the first sucker is going in this direction. As those field lines pierce the plane of this second loop, which direction am I going? I'm piercing to the... Which direction is the field from the first guy? Into what? No. You're looking at this from the edge on. That's why I'm trying to draw sort of a perspective drawing. This is not an ellipse. This is a circle viewed from the side. Perspective drawings suck. I'm sorry. 2D is hard.
This one makes sense right now.
Good. So viewed from side on, a circle that is, I'll just tell you, from my perspective, rotating clockwise, which direction is the field in the middle of a clockwise circle of current? Hold your hand. So the circulating direction of fingers is circulating clockwise this way? Yeah, the result, the field, the direction is your thumb. Curvy current, straight field, curvy field, straight current. Okay, so how about the second version? You like the first rule better. Okay, so I'm going to tell you that the current in front of the page, is down. First finger down. Now I want to know about the field. To your right, yeah. To my away. Right. So if the field is going that way, which direction is the flux there? From your perspective, it's to the right. Yeah. Is that increasing or decreasing flux? If the current is getting stronger, you're answering step 3. Is the original flux increasing or decreasing? Increasing to the right. Step 3, how do you oppose an increase to the right? It's not decrease to the left, that's double counting. The flux, the reaction flux is to the left. I'm not going to ask you if that flux, how that reaction flux changes, just which way. Correct. The reaction to an increasing right is a leftward result. Good. Wait. Yeah. Direction. Uh-huh. Because I said this part is closer to you, and where the field is inside a loop is it's in the middle. Oh. Yeah.
That makes a lot of sense.
Good. It's actually a complicated shape, but the vast majority of the field that we're interested in is inside the loop. Did y'all hear that, by the way? I walked Selena through it. Correct answers are right, increasing to the right, and to the left, respectively. You guys get that? From your perspective, a circle which is looping down in front, up and back, out on top, in on bottom, schloink, creates a rightward field. That rightward field pierces the second coil to the right. Duh. That current is increasing, the field gets stronger. A field that gets stronger to the right, the change is rightward. How do you oppose an increase in right flux with a left flux? You don't like that. Tell me why. Yes. It gets to be a complicated equation. We're not going into the magnitude as it varies. Do you know exponential function, e to the t? It's an exponential function. Questions before we go on? I'd rather that lots of people understand deeply than that everyone understands poorly and that we see. I'd rather cover a few things well than a lot of things badly. Ask me. So can you visualize that I'm looking end on a circle and the closer side to you is down? You can look at it either direction, from either side. But from your perspective, there's a circle end on. There's a circle like this, and the front side, the bigger vectors, have current going down. From my perspective now, standing on its right side, I see the field vectors, field pointing towards me, out of page, out of plane. Yeah. Mitzi, how you doing? Joanna? More or less? Yeah? Okay, so we've got increasing field to the right. We want to counter that with a leftward flux here. The last question is, apply what you just learned. How do you oppose? What direction is the current in this sucker? What direction is the current to oppose to make a leftward flux? How do you have to circulate in here? And how do you specify this? How do you specify this? This is the front side. Okay, I want you to find the direction of the current here. So tell me the direction of the current on this piece of the loop, the second loop. And again, the goal is how do we make a flux to the left, flux to oppose this increasing rightward original?
Right. That was the angle. So it has to go, well, it's not really have to go. It would go to the left.
Okay, so let's do this in 3 space. As to say in 3 dimensions. I've got a flux that I want to go left. So using the second method, I point my thumb left. I want the field to go left. Which direction are the fingers of my right hand curling? Schloink. From this perspective, they're curling counterclockwise. From my perspective, standing here, my thumb is pointing me in the nose, my fingers curl around. All right, so when my fingers are on the left side, if a clock hand is on the, right side, the outside, the front side from your perspective, if my fingers are on your front, which way are they pointing? Which way is clockwise going? This is counterclockwise, sorry. Up. Current is going up on the front side of the reaction. Yes. Because that's what we wanted from step K. To oppose it. Yes. Yes. From that side perspective, yeah. Yeah. Okay with that? I think we should slow down and hit this for multiple days. I'm going to give you answers to the quiz like literally, and we're going to extend this into next week rather than pushing forward. I'd like you to get this. Here, take a look. Wait, how do I stop share? I want to stop sharing. I want to share the quiz. Google question uno. If I give you the width, the speed, and the magnitude of field, what equation is the motional EMF equation? What is it? How would you do motional EMF if I've just got 3 pieces, B, L, and V? before we got delta phi over delta t. Where we came up with that from. BLV! You're too young to have kids, but you should multiply. Don't forget to convert units. Centimeters, microtesla, you have to pay attention to that. Here's what we just did. The people who don't come to class and don't watch the recordings are screwed. Merry Christmas, here's the answer. Here's how to do it. The battery pushes current which way? To the left. Current goes out of the plus side, comes back into the right, comes back into the minus side, yeah? If I have the switch open and then just immediately close it, am I increasing or decreasing the current? I'm increasing. I start with zero current, now I've got current. Current going into the, oh, look at the sense, the directionality of this piece of wire. This wire is going up on the back, down on the front, in on the bottom, out on the top. This direction circulating. The current is increasing in this sense. Which way do I have to curl my right hand to shrink? So if the current is if the current is going this way, circulating up on the back, down on the front, look, you have to look carefully at the diagram. The field is always to the right inside that iron core, the inside. From my perspective, that's clockwise. Yeah. Again, you have to look at the direction of the battery. You have to look at the sense of the wire around the core. If I wrapped this the opposite helicity, that would put the answer. Okay, so the magnetic field started at zero and now it's going right. Which direction do I want to oppose that with? I want a leftward flux. Which direction of current makes a leftward flux from this perspective? Counterclockwise. Counterclockwise. That it says, read the question. Immediately after the switch is closed, I'm turning it on. At the instant the switch is closed, this voltage comes into being. Yes. If it stays closed, there's no current, there's no induced voltage. If I tell you the diameter of a circle, can you find its area? How? What formula? Pi r squared. Don't forget, diameter over 2. You can find the area with this. If I give you the change in field, can you find the change in flux? Change in field times area? If I tell you the time it takes, can you find the rate of change? That's the voltage. Okay? Try this yourself. Test yourself here. What do you think? And then I want you to give me the finger. No. This is an all that apply. So it's multiple. A, B, C, D, but this is a more that apply. Okay, ask yourself, in the case of A, I'm holding a magnet near a coil. Is there flux? Yes. There's field. A permanent magnet makes a magnetic field that goes through the coil. Is the field changing? No. No induced voltage. No reaction. Just holding a magnet near a coil of wire doesn't make electricity flow. What if I shove it in the hole? The magnetic field in the loop of wire is changing. The direction of the reaction current, as we're learning today, opposes the increase. So B is a true statement. How about C? No. Magnetic field of the Earth just going through a coil. Is the field changing? Is the area changing? Is the angle changing? No, none of those is changing. There's flux, but there's no change in flux. Nothing is changing in this scenario. You don't like that. Passing through doesn't mean the coil is moving. The field is passing, the field is going through, the field is oriented along with the direction of the what's this? Last one, wire constant current. Is anything changing? No flux induced, A and C. This one, God willing, is easy, Tesla meter squared. I didn't even put. And if you don't know this, then you haven't been paying attention. There you go, there's a quiz. I'm moving this week's homework back a week so that we can actually focus on this and get good at it. I will add a couple of questions next week when I see how far we get. You are welcome. I love you. Goodbye. Any questions before we're actually out of time? But no, plug in numbers. Oh, wait, I'm so sorry. One last thing. Hey, I gave multiple turns. Wait, no. This is actually fast. If I give you multiple turns of wire, you need to know each turn picks up that voltage. Total voltage, if you've got many turns of coil, you add those voltages together. Multiply what you get directly, delta phi over delta t, multiply that by the number of turns. There, I have done the quiz for you. Yeah. That's what you will plug into